So as of Wednesday, right, that kind of wraps up our content on multi-component, multi-phase thermodynamics, right? So we went through that pretty quick in like a couple weeks or so, maybe 4 or 5 lectures worth of content, where we spanned all the way from humidity, right, which is one liquid phase evaporating into one gas phase, not a vapor phase, a gas phase, right? Because then the gas can't very readily condense into the liquid. We talked about liquid-vapor equilibrium, solid liquid equilibrium, gas liquid equilibrium, liquid equilibrium, right? So these are basically interactions of all the different phases that we would possibly encounter for a separator. Now the next biggest piece of equipment that we focus on a lot of times is a reactor. And early on in the semester we talked about how we can do the thermodynamics on a reacting system using the equilibrium constant and the mole fractions, the partial pressures. Hopefully that all rings a bell. So what all of these things allow us to do is to write new problems, in your guys' perspective of course, is to write new problems that are not as arbitrary. So now we can build an entire process where we only have to describe the thermodynamics of what exactly is going on. Then we can work through all the material balances and figure out what the compositions and flow rates are of all the streams, and it physically makes sense, right? Whether or not we can practically reach these thermodynamic limits in the time available as the fluid flows through the process is a different question. That's much more complicated to answer, and that's essentially what the entire junior year of the chemical engineering curriculum is dedicated to. So now the next topic that we will cover is energy balances, and that's about the rest of the class, right? But it's a lot to talk about. So what we're going to be doing now is talking about the energy balance, integrating it into existing processes, and then throughout the rest of the semester, we're just going to be making the problems a little bit more comprehensive, a little bit more comprehensive, and a little bit more comprehensive. So ultimately, the project will be integrated, detailed material balance calculations over an entire process. But I have yet to write it, so I don't have it assigned quite yet. Now the energy balance is one equation. That's it. Right? With material balances, we had one equation per independent species, right? With vapor-liquid equilibrium, we had a vapor-liquid equilibrium expression for every single species in the system. With the energy balance, it's just one more equation, right? But the problem is generating the data to put into that equation is the tricky part. So, who has had thermodynamics 1? Just about everyone. Good. Okay. Some people skate around the requirements and say, oh, I'll take it next semester and things like that. Okay, so as I see, virtually everyone has had Thermo 1, which is good. Because the hard part of energy balances is not the energy balance equation itself. That is actually pretty easy. The hard part is getting the data to put into the energy balance, which will take a lot more time. So, the first little bit that we're going to go over should hopefully be a review. So, forms of energy. Now, this discussion is going to focus on forms of energy that we will most typically see as chemical engineers, but this is not the all-inclusive energy form. So we have obviously kinetic energy. And again, in chemical engineering, I don't know how conventional this is across other disciplines, but we typically write velocity as lowercase u, because v as volume is a bit confusing. Now this is the energy of a particle with mass m traveling at velocity u. What we are going to be most interested in though, however, is for an open system that is flowing. And so what we care about is generally the rate of energy transferring into or out of a system. And in this case here, we'll write this as 1/2 m dot u squared. So the E dot is going to correspond to joules per second. The M dot is, of course, kilograms per second. So this is a rate of power input. So we could also think of this in terms of watts, right? Joules per second, kilojoules per second, megajoules per second. Same thing with potential energy. Now, potential energy, there's lots of different forms of potential energy. There's electric potential energy. We're specifically focused on gravitational potential energy. Now, where we would see this, right, this is the energy that a object would have if I picked it off the ground, raised it up. That's the potential energy that it has, right? I gave energy to that particle by lifting it up. Now, this term right here might seem a bit more complicated to employ, but really this is the term that hydroelectric power plants are built on. You have some z height that the water is flowing through the dam, from the top of the dam to the bottom. You have g, the gravitational acceleration, and you have a mass flow rate of the water going through the turbines in the power plant. Right? This is the basis for hydroelectric power. And lastly, the one that we care the most about is internal energy. U, which has units of joules. U with a little hat on it is something we'll use very commonly. Is joules per kilogram. And U dot, which would be joules per second, the rate of internal energy entering a system. As chemical engineers, which of these three forms of energy do we care the most about? Internal energy. How much more important is internal energy than these two? A little bit or a lot? A huge amount. So much so that we don't really even care about these two terms. And let's think about this a slightly different way, okay? What if we wanted to power our car using gravitational potential energy or kinetic energy?
You'd always go downhill.
Well, let's say we had some elaborate system of weights somehow that you got out of your car and you cranked them up and then you started them up. You would not get very far. The amount of energy stored in kinetic energy, the amount of energy stored in potential energy is very, very, very small. Same idea as could you run your car on a pressurized tank of fluid or gas, like hydraulic pressure? No, not nearly enough energy. Now, if you were to calculate the amount of internal energy that you're putting into your vehicle when you fill it up with a tank of gas, right? You're putting energy into your car at a rate of gigawatts, right? The energy stored in chemical bonds and in intermolecular structures of molecules is vastly higher than kinetic and potential energy. So in general, we completely neglect these. Now that's not necessarily a universal rule. Obviously, if you were doing a hydroelectric dam, you have a huge mass flow rate of water going through the system. And you have a huge potential energy difference because these dams are very, very large, like the Hoover Dam or the Glen Canyon Dam. Right? But for us, for most chemical plants, that's not reliable enough. So instead, we power everything by burning fuels or relying on exothermic reactions in general. Right? So in general, as chemical engineers, we care about U, the internal energy. Now, the internal energy is the velocity of molecules, it's the vibration of atoms, it's the interactions between two atoms getting near together or far apart from one another, and it's the energy stored. I think I said bonds already. I don't know if I said that already. But that's how the U energy is stored. Now, a couple of definitions. We have open systems, and this is where mass enters or leaves. We have closed systems. Hopefully these are not shocking definitions. Heat and work. Heat-driven flow is driven by a delta T, right? So if one object is hotter than the other, you have a flux going into the system by convection, conduction, or radiation. And work, mechanical energy in or out. So work, there's a number of different forms of work, right? You can have expansion work, right, where the system physically expands. It's like a balloon, right? A balloon doesn't spontaneously push back the atmosphere and inflate itself, right? You have to put energy into that balloon to inflate it. Work could also be a pump impeller, spinning and heating a fluid up. Or it could be the opposite. It could be a turbine where the fluid is spinning it and it's pulling out electrical energy. So there's a number of different forms of work. But in general, we just draw this generic W to account for all the different forms of work. And lastly, adiabatic. And this is no heat in or out. So work, we have as W, heat is Q. That's a pretty universal notation. So let's go back to our general balance equation. In minus out plus generation minus consumption is equal to the accumulation. What terms can we cancel out always in the general balance equation for energy balances?
Accumulation.
Generation and consumption, right? Energy cannot be created or destroyed, so we have to conserve it. So whatever is the imbalance of in versus out is how much stays inside the system. Now that would be the integral form, or sorry, not the integral form, the difference form of the balance equation, right? We're looking at the rate of stuff in, the rate of stuff out, and the rate of accumulation. For a closed system where we're going to start off, this is driven by sort of the initial, the final, and the accumulation. Like imagine it as a bucket, whatever you put in, whatever you take out, the rest is left there as an accumulation term.
If it were a closed system, though, wouldn't the accumulation just kind of be like the change that has occurred in energy?
Yes, yeah. So in a closed system, the change would be over a period of time. So for closed systems, we often use the integral form of the balance equation, right? Where we integrate these over some period of time, going from some initial state I to some final state, some initial state to some final state, and some initial state to some final state. So if we look at the closed system energy balance, oops, got that better. This is our general closed system energy balance. We call this delta U, delta kinetic energy, delta potential energy, Q minus W. And for the most part, that's going to be 0, and that's going to be 0. We're not going to care about those terms. Now, this part right here warrants some discussion. I have a plus Q and a minus W. Is this the same convention you guys have seen previously? This is a hotly debated topic, but it doesn't matter. And I don't care which convention you use, and I promise you I will not stick to a single universal convention. Because if we were to draw our world-famous piston cylinder device, right? We have some material in here with some initial internal energy. After some period of time, there is some final other internal energy. Now with Q, typically we draw a dashed line indicating that this is not an actual mass flow rate into the system, it's a energy stream going into the system. And then oftentimes, we'll draw the work going out. Now this is a convention that goes back hundreds of years, because the whole purpose of thermodynamics is to basically predict how can we optimize steam engines and heat engines, right? If I'm buying a ton of coal, I want to be able to make as many textiles as I can in, late 1700s and early 1800s in England. So I'm going to burn a bunch of coal, put a bunch of energy into my system, I'm going to design a process and extract the most amount of work. So by following that convention, that's why we always typically have Q going into the system and work going out. You want work out. But I don't care. How I've drawn this system here adheres to this convention. But instead, I could draw work going into the system, and I would just change that to a plus. Now, the reason why you don't want to lock yourself into thinking only one way about how this works is because when you have multiple processes, let's say like a heat exchanger, right? We have a hot side of the heat exchanger, and we have a cold side of the heat exchanger. All right, and we're transferring energy from the hot side to the cold side. But this is a multi-unit process. I have to draw an arrow with the heat transferring from one fluid to the other. Now, in this circumstance, I told you this is the hot side and this is the cold side, so we could assume that it would go this way. But when the processes get more complex, you won't necessarily know which is the hot side and which is the cold side per se. But in this convention here, if I were to do an energy balance on this system, I should minus my Q. Oh, that violates this convention here again. And on this side, I should plus my Q. And if you keep the arrows in and out consistent, then you don't have to be changing positive and negatives from doing a balance on one system to the other. And that's going to be the key critical part, which takes, because let's say, for example, we were to change the convention halfway through. That means it would matter whether or not you did a total balance, a hot balance, or a cold balance, how you have a plus or minus, and you're just going to throw things off badly. There's a question over there? Or?
Yeah, well, I was just going to ask if you stuck to the Q minus W, but you were actually putting work in, it would just be a negative, minus a negative.
Absolutely, it would be a no big deal whatsoever. So let's say we completely botch this and we draw our arrows in completely the opposite directions. Your end result will tell you that you're wrong because it would just be a negative sign. And a negative heat in or out just tells you that you drew the arrow the opposite way. That's it. And so whenever I ask questions about work in or work out or heat in or heat out, I don't care about the positive or negative sign. What I prefer is an absolute value and saying it's going into or out of the system. That, I think, is the more clear explanation of what's going on, as opposed to, I don't know, wrapping people on the wrist about, oh, it's a positive work versus a negative work. So, of course, we have the approximations here. Work could be 0, the system could be adiabatic, and that simplifies our calculations quite a lot. Everyone has seen closed system energy balance, right? What about open system energy balances? Are we comfortable with that too? Like expanders, turbines, compressors. Have you guys done those types of energy balances before? Okay. That is where we're going to be living for the most part. Okay, now open system energy balances introduce slightly more complexity. So as I mentioned here, in open systems, we're typically going to be dealing with the rates of energy in and the rates of energy out, which is exactly parallel to open system energy balances, where we care about the rate flowing in and the rate flowing out. Now, although you may be dealing with a system that is a continuous system, you can always kind of approximate it as not a continuous system, which is basically what we're doing. We're assuming a basis, right? So I don't want you to think that these two differences are kind of like completely different and you should never intermix the two concepts, because when you assume a basis, right, you can also kind of assume that you're performing a continuous system over a period of time, over of a second or a minute or an hour, right? But anyway, so when we talk about an open system, we typically use enthalpy. Now, it's important that we have a discussion on what exactly enthalpy is and why it matters. So what is the definition of enthalpy? So it should be a well-structured equation. It's U plus PV. So, the key thing to remember about thermodynamics, and this is something I stress very, very heavily in the graduate thermodynamics class I teach, right? So I teach the MS students and PhD students thermodynamics. There are 3 fundamental variables to the universe: V, U, and S. Everything that we work with beyond V, U, and S, basically, right? U and the first law basically say that we cannot create or destroy energy. S and the second law means entropy always increases. And V, because we live in a universe that actually has real 3D volume. Right? These are the 3 base units of the universe. Everything else in thermodynamics is a made-up number. Everything. You could, in theory, reconstruct all of thermodynamics with an entirely different set of made-up numbers. The reason why Gibbs free energy is so nice and so convenient is because temperature and pressure are so nice and so convenient to keep constant. Right? But you could imagine an alternate universe where different variables were held constant, and you have a completely different formulation of thermodynamics. So what I want to get inside everyone's head is that thermodynamics is an arbitrarily constructed field of study. Every number you deal with is a made-up definition. But all of those definitions are very, very convenient. So when I teach thermo, I emphasize that you are not learning the answers, you are learning the system. Right? What we're doing is we're unpacking the system that has been developed for hundreds of years that allow us to organize complex information about how energy flows from one position to another in the form of reactions, heat, so on and so forth. And then you are learning how to unpack that information to solve questions. Right? Thermodynamics was developed in the 1800s and 1700s. That's why some of the conventions seem weird. Internal energy was literally just internal energy. We didn't know that atoms existed back when this law was developed and this definition was formed. We didn't know how matter stored energy. We just knew that this block of something had more energy than this block of something. But we didn't know if it was the bread pudding model of the atom or whatever other different structures of the atom were. Right? Atomic theory didn't really develop into the late 1800s and early 1900s. Thermodynamics predates it by almost 200 years. Okay? So everything we're talking about is the system, right? That's why it seems silly. That's why it seems arbitrary, okay? Is because it is. But it's a very, very, very useful form of silliness and arbitrariness. Is there a question?
I was going to say, don't all of these arbitrary definitions, the reason that they describe reality well is because at the heart of them, they actually go back to the energy and entropy that you said are
exactly.
So even if they may not have terms that include entropy in them, the reason the equation works is because of entropy, even though it's not.
You're 100% correct. So for example, equilibrium in thermodynamics is given by when entropy is at a maximum. That is the equilibrium criteria for a system with constant volume, constant energy, and, well, entropy always increasing. Right? That is our universe, right? Our universe has a finite amount of energy, right? And let's just say it's semi-static, and the universe has a constant volume, right? So at equilibrium, S equals a maximum if U and V are constant. Okay? Now this directly corresponds to when Gibbs free energy is a minimum, but if P and T are constant. But this criteria here, where what we are conventionally used to, right, when the Gibbs free energy is minimized at constant pressure and temperature, this directly traces back to this as the same criteria. So what we're doing is we're just building up on these units that, well, quite frankly, we can't measure and are impossible to measure, right? We have to infer what U and S are. We can measure V, right? But what we're doing is we're taking these units that form the foundation of thermodynamics and we're translating them into units that are more easy for us to measure in a laboratory. So it's a bit of an aside, but hopefully this is not totally off in left field and you've seen some of these terms before. Who's heard of the Gibbs free energy? Okay, so most people, okay. So we're not totally off in left field. Now enthalpy is a super useful thermodynamic state function, right? And it's because of open systems is why we use it. So, if I have a stream flowing into this process, and I drew it as a pipe, right? If I have a stream flowing in and a stream flowing out, right? If we neglect the kinetic and potential energy, right? Our system is this box here. So when I perform an energy balance on this box, I have to consider what is the rate of energy flowing in, what is the rate of energy flowing out, and the imbalance there is either going to be an accumulation or some heat or work loss term. So as my energy flows into this system, the molecules that flow in bring with it bond vibration, bond velocity, the energy stored in chemical bonds, right? And as stuff flows out, some of those molecules take that energy away. So if I was putting heat into this system, you would expect that the internal energy coming out would be higher if your net accumulation was 0, right? But it's also doing something else. When the energy is, when material is flowing into the system, it's physically having to push the volume in and out of the system, right? So in order for this fluid here to make it into the system, the flow has to push some volume element into the system. And the only way it can do that is with some sort of a fluid pressure. Right? So you can imagine that the fluid here is squeezing in that fluid and forcing it to flow into that system. So not only is the fluid bringing with it the energy stored in its molecular state, it's also physically pressurizing the system a little bit. That's what this PV here is. And likewise, when it flows out, the system has to push out that fluid. And it pushes out that fluid by physically squeezing that fluid out of the system. So that's why for open systems, we always use enthalpy. Yes?
So for continuous systems with no accumulation and the tubes are the same diameter, can you assume that the two pressures are the same?
If there's no heat or work going in and out, then yes, because obviously then your energy balance would say that in is equal to out. But if you have heat going into the system and you make this system higher, that'll change the enthalpy of your system a little bit. Right? So it could potentially be different. Now, this is something that your thermodynamics teachers probably do not want me emphasizing. Which of these two contributions to enthalpy is the biggest? It's you. The contribution of enthalpy is actually not that big. So if you carried out your entire life confusing the concept of enthalpy and entropy, enthalpy and internal energy, your calculations would not be that far off. They would not be that far off, right? Because in general, enthalpy is something that's pretty easy to find in tables. Sometimes it's actually kind of difficult to find internal energy for certain tables, right? We use enthalpy a lot more than we do internal energy. But like 99% of it, maybe not 99, but a good chunk of it is all internal energy, right? So even if you get confused, it's better to just use one of the two numbers than it is to do nothing, right? So enthalpy itself is physically pushing the fluid in and pushing the fluid out, because that's giving the system a little energy and taking a little energy out of the system. Now, with that being said, for most of the calculations that we're going to deal with, let's look at this PV term. Right, so let's take a second. PV is equal to, we're going to have pascals times by meters cubed. A pascal is a Newton per meter squared. A meter cube is a meter cubed. And so this turns out to be Newton meters, which is a what? Joule. It's a joule. Everything works out. Right, and that's why I only remember one ideal gas constant, 8.314. Because 8.314 is the units of joules per mole Kelvin. Great, I can use it in energy balances. But wait, it's also pascals meter cubed per mole Kelvin. Oh, now I can use it in equations of state. So I remember exactly 1 unit of R. Now let's think about this PV for an ideal gas. What is PV equal to for an ideal gas? nRT. For an ideal gas, what is the enthalpy a function of?
And
Yeah, of course, yeah, and yeah, more material,
but temperature?
more energy. It's just temperature. It's only temperature, right? For an ideal gas, the internal energy and enthalpy are only a function of temperature. For a real fluid, this is not the case, right? So for a real fluid, the enthalpy is different as a function of pressure and temperature. And so if you look at your steam tables, you'll notice that the enthalpy indeed does change when you change the pressure. But for an ideal gas, which is going to be the lion's share of our calculations, the enthalpy and internal energy are only functions of temperature. Now, the main reason why that's the case is sort of committed to more of a advanced thermodynamics class. Okay, so let's write out the open system energy balance. Now, I'm going to just commit to, since everyone seems to be somewhat familiar or fairly familiar with the energy balances from your thermodynamics class, so we have to thank your Thermo 1 teacher, we'll just write out the open system energy balance. Okay. Generally speaking, we're going to write the open system energy balances in minus out equals accumulation. Let's start off with the accumulation part. How should I, for, let's say, this system here, and I'm going to draw a positive work going in this time, right? And let's assume I have multiple streams coming in and multiple streams coming out. Okay? So this is my system. This is my balance. I have pipes flowing in, pipes flowing out. I have heat coming in. I have work coming in. I have work coming out. Who knows what's going on? How would I mathematically write my accumulation term?
Like with the variables? Or
Yeah, with variables that we have on this board right here.
so it'd be the kinetic energy.
So let's only focus on internal energy and enthalpy. So let's just throw kinetic and potential energy out of the way.
Du by enthalpy?
du dt, correct. Right? This is the rate of accumulation of energy of our system. Now, if we wanted to be more diligent, right, we could of course write dE dt, which would be equal to d dt of U plus the kinetic energy plus the potential energy, right? And we could go through this exercise and we could write out, oh, the total energy includes the kinetic and the potential, and then the flowing in has kinetic and potential, and the flowing out is kinetic and potential, right? But we're never going to be using it in this class too much. But know that if I do ask you a question about how warm does a ball get if I take a rubber ball and I drop it from this height and it falls and it hits, right? You could calculate how much energy goes into heating up that material by using the potential energy, right? So know that these exist, and hopefully you covered them in your Thermo 1 class well enough, because we won't spend a tremendous amount of time in class talking about it, because that's not the difficult part of energy balances. So, now all we're doing with an energy balance is exactly the same thing that we did with a mass balance. We're just accountants. We're keeping track of what's flowing in and what's flowing out of the system. So, let's take care of the easy ones. We have Q and we have W. So I'll just write Q dot plus W dot. And how I've drawn the arrows, that's exactly how I should be writing my material balance, right? Because I could have a separate process over here where the heat and work are coming from. And I want to keep track of which direction things are flowing in. Now, the next thing we have to deal with is our mass flow rate streams, right? We could have stream 1, stream 2, stream 3, stream 4, however many arbitrary streams that we'd want to label. Now, these are flowing into the system mass. Mass innately has energy associated with it. Now, there's of course like, E equals mc squared, right? That kind of energy, but that's a nuclear process, we're going to neglect that. But what we do care about is the energy stored in the bond vibrations, molecular rotations, molecular translations, right? All these different forms of energy of molecules wiggling around and bouncing off of each other. And for that, we contain, that's internal energy. But it's a flowing system, so in order to physically get that internal energy into the system, it's got to have a push. That's the enthalpy. So the energy flowing into our open system is a summation of all the enthalpies flowing in and all of the enthalpies flowing out. So what we're going to write right now is summation of all of the enthalpies flowing in, the rate of enthalpies flowing in, minus all of the enthalpies flowing out. Right? This could be for streams 1 and 2. This could be for streams 3 and 4. Now, this is not generally how we write this expression. Well, let's double check the units. This is joules per second, joules per second, joules per second, joules per second, and joules per second, right? H dot, H has units of joules. The dot over the top means flowing in and out of the system. Yes?
So when you write H dot, that would be like U plus PV dot. Is
Correct. So
so
H
it's
dot,
the
U dot, PV dot.
Okay, got it.
Pressure is a intrinsic property, so you can't have it changing as a function of time like that. So this is not how we generally write it, though. So what we want to do is break down this expression here into a form that's a little bit easier for us to actually implement. So we're going to keep the summation of everything flowing into the system, but we're going to break this H dot into a mass flow rate times by an H hat. Right? So we can put little brackets around this and say flowing in minus the summation of M dot H hat. Put little brackets around it, flowing out. And this is the form of the open system energy balance that we will be using excessively. Now let's break this down right here. So M dot, remember, is some mass flow rate per unit time. This could be pounds mass per hour, could be kilograms per second. The H hat is equal to the energy per kilogram, or you could also think of this as per mole as well. It's a specific enthalpy. And so the product of these two terms gives us joules per second flowing into the system. Now, this H hat, same thing like U hat, this is what's tabulated in your steam tables, right? Enthalpy, internal energy, Gibbs free energy, entropy, these are all extensive properties. The more material you have, the more entropy you have. The more material you have, the more chemical bonds you have, the more energy you have. Right? So instead, we care more about what is the energy per unit mass. Right? So that's the material property that we're going to be calculating. Now, if we were to bust out an example of an open, steady state system using only steam, right? Who here has used steam tables before? Everyone. Who here has used this equation before? Virtually everyone, right? So if I were to give us a question saying, oh, liquid water enters at this pressure and temperature and it leaves as superheated steam at this temperature and pressure, the process is adiabatic. The process is no work. What is the heat energy input? I think most people could figure that out right now, right? You would just have to look up in your table, what is the enthalpy flowing in? Liquid water at some temperature and pressure. Look out the outlet, what is the enthalpy coming out? The superheated steam at some temperature and pressure, and then you just plug and chug these numbers away, okay? So this is why I say that the energy balance equation is not the difficult part. All the calculations we're going to do, we will not have tables available to do the calculations. The difficult part for us is building our own tables to get out the specific enthalpy values for the materials of interest that we care about. CO2, ethane, right? benzene, toluene, right? How much energy does it take to do a flash separation? What's the heat of vaporization of a certain compound as a function of temperature? That's going to be the difficult part. So thermodynamics tells us the system that we can unpack very small amounts of data that someone has measured in the laboratory and use it to predict the behavior of systems far beyond the conditions where they were actually measured. Right? That's the key of what we're going to be talking about, is calculating enthalpy values. That is what we're going to be devoting the next several weeks of the class to, is just this one concept here. Because this equation, most everyone has applied before. Right, so if we go back to the example that I mentioned, where we're boiling steam. So let's say we are boiling steam and we have access to the steam tables. Let's take our open system balance and write out how we would actually solve that particular problem. So, steam generation. So we are going to have some liquid water stream entering the system at some temperature and pressure. We are going to have a boiling unit, and it's going to leave out as steam at some temperature out and pressure out. I'll call it in there. And we're going to accomplish this task by just putting heat into it. We're going to have some mass flow rate of water in and some mass flow rate of water out. Now, our material balance would tell us that in equals out, so that's taken care of. That's the trivial part. So let's simplify our open system energy balance. So let's start off. du dt. What is our first approximation that we always use for flowing systems?
du dt is 0.
Bingo. du dt is 0. This corresponds to a steady state process. There is no accumulation. So the energy balance works out perfectly so that no net energy goes into the system. Now let's go next. What's next? We have Q. Yeah, we still have a Q, and it's still positive, so I'll still draw it as a positive Q. Work, we don't have any work. Flowing into the system, we do have some energy flowing in. We have the mass flow rate of the water times by the enthalpy flowing in minus the mass flow rate of water times by the enthalpy coming out. Now what we can do is we'll just simplify this expression a little bit. Right? And then what we care about is we care about Q, right? We know how much steam we need to generate for this process. We just need to figure out how much energy is it going to cost us to make the steam. So we'll solve for Q by moving this to the other side of the equation. We get Q is equal to m dot, but in this case, it's h out minus h in. And how do we typically write this? Bingo, delta H. Q dot is equal to m dot delta H hat. Now this is probably what most people have seen for an open system energy balance. And the confusion is always, oh, well, I'm really confused, right? Because I know that Q is equal to delta H for an open system, but I also know that Q is equal to delta U for a closed system, right? Please get this out of your head. It's not as simple as closed is delta U and open is delta H. What the more important aspect is, can you take this general energy balance and come up with both of these two expressions? That's the key part, right? And we're going to do that in the next 3 minutes of class, right? So this notation here, where we go from a summation of H's in and H's out to a delta H, this is a infrequent occurrence that you will encounter, right? Because a lot of the systems that we care about, are not just one stream in and one stream out, right? They're going to be multiple streams in and multiple streams out. So this convention, where you're adding up the ins and minusing the outs, is a better way to go than the delta H here for a more complex problem. This is only going to be applicable for a simple open system, one stream in, one stream out. So this convention of delta, meaning out minus in, is not necessarily going to be the case that we can always rely on. Okay, so the last thing I'd like to do is take this equation here and regenerate the closed system energy balance, where we instead are getting the delta U expression. So we're going to start off with our full form energy balance for the open system. Okay. What can we simplify in this expression if it is a closed system?
It's equal to U plus PV, can we do that?
Not yet. This is our energy balance for the open system and for the closed system. It's just hidden. We'll find out where to look for it. So m dot is 0. So this one goes away and this one goes away. So what we're left with for our closed system is du dt is equal to the rate of heat in plus the rate of work into the system.
Why is m dot 0? Why is m dot h?
Oh, m dot is 0 because this is closed system for this balance. In a closed system, no mass can enter or leave the system, so your mass flow rate has to be 0. Now, how do we get this equation to look like this equation here? We integrate it. Right here I've written T1 and T2, but more often than not in thermodynamics you'll see the expression state 1 to state 2. Right? These are just magical terms basically saying, yeah, from some point to some other point. Right? And with thermo, they're state functions, so we can control the pathway. Right? But in general, thermo math is sort of the funnest calculus you'll ever have to deal with. Right? Because it's a little bit sloppy, but it always kind of works out. Right? So if I integrate du dt, I just get delta U, right? That's the net change of internal energy of the system. I'm integrating all of the small changes over a period of time to give me an overall big delta difference, okay? Integrating Q dot, well, if Q dot is constant, right, if the rate of energy input is constant, then it just turns into the total. Actually, it doesn't even have to be the total, it's constant, right? I'm integrating the rate, which gives me the total amount that has entered and left over a given period of time. And the same thing with work. So now this internal energy here, you can also rewrite this as the mass of the system by some average internal energy. And we get m dot delta U is equal to Q plus W. We're not exactly at the same expression that we had here, partly because I need a little hat on that equation. But in order to get that expression, we can split it into two ways. If work is equal to 0, therefore our m delta U is equal to Q, which is the closed system energy balance that maybe an introductory thermodynamics class would like to have you memorize. The other option here is, let's say work is equal to minus PV, right? That's the expansion work of the system. In which case we'll get m delta U hat is equal to, put a hat on that one there, Q minus PV. Let's see, let's get rid of this, let's say this is 1 to make my math work out nicely. But then if we rearrange this expression, we can also find that delta H is equal to Q for a closed system, right? So delta H is a useful variable even in a closed system. It doesn't have to be this rule of U is for open systems or closed systems and H is for open systems, right? This procedure that we did right now on the board, this procedure here is basically what everyone should commit to the memory of the process. Right? I don't want you to just memorize a rule for a particular system and a particular energy balance. Always start with this expression here and simplify it down. You can simplify this expression for an open system, for a closed system, for integral form, for differential form. Right? But this one here can be used for every system that we'll use in class. And the last thing I'll say is remember, this is where we're going to be spending all of our time, is calculating the enthalpies. Because if we had all of our problems with steam tables, I'm sure everyone could apply this equation right now, right today. All right. Have a good weekend. See ya.